In the far reaches of our solar system, beyond the orbit of Neptune, something unusual is happening. A mysterious force is pushing around icy objects, and clusters of these objects have unusual orbits that can't be explained by the known planets alone. Scientists think this could be caused by a massive hidden planet, often called Planet 9. First suggested in 2016, this potential new planet has fascinated astronomers. Interestingly, this isn't the first time a planet has been proposed using mathematics. Neptune and Pluto were both discovered because their gravitational influences were predicted before they were seen through a telescope. Astronomers noticed irregularities in the orbits of Uranus and later in the Kuiper Belt objects, leading to the discovery of these distant worlds. A century later, we find ourselves in a similar situation with Planet 9, following this fascinating tradition of using mathematical predictions to uncover hidden planets. Some researchers believe it might have been a rogue planet captured by our Sun's gravity, while others think it could have formed from the same disk of gas and dust as the other planets. If Planet 9 exists, it is believed to be 10 times more massive than Earth and orbit the Sun at a distance of 400 to 800 astronomical units, which is 400 to 800 times the distance between the Earth and the Sun. Astronomers have been eagerly hunting for clues, using powerful telescopes and advanced computer models to track its influence. After years of watching the sky, solving mathematical equations, and running complex computer simulations, they now have the strongest evidence yet that Planet 9 really exists. This discovery introduces an exciting plot twist in the story of the hidden planet. So, what evidence did the researchers uncover in their hunt for Planet 9? If we have found exoplanets hundreds of trillions of miles away, why has it been so challenging to detect Planet 9 directly in our cosmic backyard, even with some of the most powerful telescopes at our disposal? Finally, and most importantly, if Planet 9 really exists, how did it end up being so far in the outskirts of the solar system? Before we begin, make sure to subscribe to our channel for regular space updates. Although Planet 9 was first proposed in 2016, its story began soon after the discovery of Uranus in 1781. Over the years, astronomers noticed something strange. Uranus wasn't moving exactly as their calculations predicted. It seemed to speed up and slow down in its orbit, hinting that there might be an unseen force acting on it. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch-Adams in England, independently suggested that the unusual movements of Uranus could be caused by the gravitational pull of an unseen planet. They used complex mathematics to predict where this invisible planet might be located. This was a bold hypothesis, relying solely on mathematical calculations to propose the existence of an unknown world. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant pointed their telescope to the part of the sky Le Verrier had indicated. To their amazement, they found Neptune on their first night of searching, very close to where it had been predicted. This was a remarkable achievement, as it was the first time a planet had been discovered through mathematical prediction rather than by chance observation. After the successful discovery of Neptune in 1846, astronomers thought they had a complete picture of the major planets in our solar system. However, when they tracked Neptune's orbit, they found that Neptune, much like Uranus before it, exhibited slight deviations from its predicted path. These irregularities were subtle but persistent. Given the success of using gravitational influences to predict Neptune's existence based on the orbit of Uranus, astronomers wondered if a similar method could reveal yet another planet even further out. This led to the discovery of Pluto after more than 8 decades. On February 18, 1930, Clyde Tombaugh, a young astronomer at the Lowell Observatory, identified a faint, distant object moving against the backdrop of stars, confirming the presence of a new celestial body. Initially hailed as the long-sought Planet X, Pluto was later found to be much smaller than expected. Pluto's mass was insufficient to account for the gravitational anomalies observed in the orbits of Uranus and Neptune. This meant that something more was out beyond the orbit of Neptune that hadn't been discovered yet. In 1951, Dutch-American astronomer Gerard Kuiper predicted that there could be not one but several icy objects beyond the orbit of Neptune, and Pluto was just a part of that bigger belt of objects known as the Kuiper Belt. The first direct observational evidence of Kuiper Belt objects or KBOs came in 1992, when astronomers David Jewitt and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This discovery confirmed the existence of a population of objects in the region Kuiper had predicted. It was rapidly followed by the identification of hundreds of more KBOs in the 1990s and 2000s, confirming the Kuiper Belt as a significant part of our solar system. As more objects were discovered beyond Neptune, the term trans-Neptunian objects or TNOs was introduced to encompass all objects orbiting the Sun beyond Neptune. TNOs are a broader category that includes any small body in the solar system that orbits the Sun at a greater average distance than Neptune or 30 astronomical units or AU. An AU is the average distance between the Earth and the Sun. It's about 150 million kilometers or 93 million miles. As the catalog of known KBOs grew, the idea of a single massive planet X fell out of favor. Astronomers began to believe that the cumulative gravitational effects of these many smaller bodies could explain the irregularities in Neptune's orbit. But then, something interesting happened in 2003 that changed the focus entirely to Planet 9. Astronomers discovered Sedna, a distant TNO with an extraordinarily elongated orbit. Sedna's orbit is one of the widest known in the solar system. Its aphelion, or its farthest point from the Sun in its elliptical orbit, is located 937 Australian dollars away. That's 31 times the aphelion of Pluto and 19 times that of Neptune. Sedna's perihelion, or the closest approach to the Sun, is just 76 Australian dollars away. This means that Sedna takes 11,400 years to orbit the Sun as compared to 248 years of Pluto. This is something weird. There are two problems. First, if Sedna formed in its current location, it would imply that the Sun's protoplanetary disk originally extended to at least 75 Australian dollars, which is on the upper end of what is typically accepted. Second, for Sedna to have formed from the accretion of smaller bodies, its original orbit must have been almost circular. Highly elliptical orbits, like the one Sedna currently has, would result in two violent collisions, preventing the aggregation of material necessary to form a large body like Sedna. This suggests that Sedna's highly elongated orbit resulted from a gravitational interaction with another massive object after its formation. The discovery of Eris in 2005 added to this intrigue. Eris, another large TNO with a highly elliptical orbit, has a perihelion of about 38 Australian dollars and an aphelion of about 97 Australian dollars. In the next few years, more extreme trans-Neptunian objects or ETNOs were discovered, and this is where we get the first and one of the most substantial evidence of Planet 9. There's something unusual about the orbits of ETNOs. Let me explain with a simple example. Imagine you scatter dozens of marbles on a flat surface. Normally you would expect the marbles to be spread out randomly. But if many of the marbles are oddly clustered in one specific area, it would imply that some force or factor is pulling them together. This scenario mirrors what scientists have observed with ETNOs. Their orbits are not randomly dispersed but rather show a clustering. Usually, if TNOs were orbiting randomly, their paths around the Sun would be spread out in all directions just like the marbles in our analogy. Their closest approach to the Sun, or the perihelion points, would be at different points in the sky, not bunched or clustered in one area. However, their perihelion points tend to be clustered in one part of the sky. This clustering is highly unusual and suggests that there is a common factor influencing their orbits. The fact that they are grouped together in one region implies that something is affecting their paths. Additionally, the long axes of their orbits, the lines connecting their closest and farthest points from the Sun, are aligned in a way that is statistically unlikely to happen by chance. This alignment further supports the idea that an external force, possibly the gravitational pull of a large, unseen planet, is at work. The consistent orientation of these orbits provides strong evidence for the hypothesis that Planet 9 is exerting its influence from afar, shaping the orbits of these distant objects. Building on the discoveries of Sedna, Eris, and 2012 EP113, along with other TNOs, the hypothesis of a distant, undiscovered Planet 9 gained significant momentum. In January 2016, astronomers Konstantin Batygin and Mike Brown published a groundbreaking paper that further solidified this theory. They analyzed the orbits of 6 distant TNOs and suggested that these patterns could be explained by the gravitational influence of a previously unknown planet. They proposed that this hypothetical Planet 9 would be about 10 times the mass of Earth and orbit the Sun in a highly elliptical path, ranging from 400 to 800 astronomical units. When Neptune was discovered, it happened remarkably quickly. Astronomers located it on the first night of searching based on mathematical predictions. This raised the question: why hasn't Planet 9 been similarly easy to find? Why hasn't it been spotted after all these years, despite growing evidence of its gravitational influence? The key lies in the vast distances involved and the faintness of the object. At such extreme distances, Planet 9 would reflect very little sunlight, making it incredibly faint and difficult to detect with even the most powerful telescopes.